Okay, in this example, we'll take a look at equivalent resistance, that's resistance in series and parallel, and its application in circuit analysis. So let's do two problems. Let's find the equivalent resistance seen from terminals A and B for this particular circuit. So we have terminal A, terminal B, and our goal is to figure out what the resistance is as seen from here. Okay, all right. So for this particular circuit, let's take a look. We see that 10 ohm and 8 ohm are in series. We also see that 5 ohm and 15 ohm are in series. So let's combine them. So we get 10 and 8 combined together get me 18 ohms. 18 ohm combined together gives me 5 and 15 ohm combined together gives me 20 ohms. Okay, so we have 18 ohms and 20 ohms. Now if you look at this carefully, you'll find that the 20 ohm and this 20 ohm are actually in parallel with each other. Similarly, you'll find that this 9 ohm and the 18 ohm resistors are in parallel with each other as well. So 18 and 9 ohm parallel resistors give you a total of 6 ohms. 6 ohms right here. That's the parallel resistance. 20 and 20 resistance gives you 10 ohm parallel resistance. Now in this circuit, the 10 ohm and the 16 ohm, these two are in series. Similarly, the 14 and the 6 are also in series. So what that gives us is a total of 16 ohms in parallel with 48 ohms. So 16 ohms parallel with 48 ohm gives us a total of 12 ohms. And the 6 ohms in series with 14 ohm gives us a total of 20 ohms. So what we're left with is 20 ohms based on these two, and 12 ohms based on the fact that 10 plus 6 is 16, and 16 and 48 are in parallel with each other. So that gives us 12 ohms. So when I look at it from this terminal right here, AB, 20 ohm is in series with 12 ohms. So what we get is RAB is equal to 20 ohm plus 12, which is equal to 32 ohm. So here's an exercise in finding the equivalent resistance. For our next example, we'll use a combination of series and parallel resistances to find voltages in a circuit. So in this particular circuit, we're asked to find the voltage across these two nodes right here, we call V1, and V2 between this node and this node. Okay, and we're asked to do this by combining series parallel circuits. So let's get started. So what we notice is that the 25 ohm and the 5 ohm, they're in series. That'll give us 30 ohms together. So we get 30 ohms right here. Now in this circuit, what we see is that 30 ohm and this 30 ohm are actually in parallel, and that gives me 15 ohms, and that gives me 15 ohms in parallel with 10 ohms, which leads me to a total of 6 ohms. Now the 6 ohm, this 6 ohms and this 12 ohm are all in series, so a total resistance of 24 ohms. Our power supply is 12 volts. The total resistance seen from the power supply is 24 ohms, so we get a current of total of half a amps. So we get a total current from the power supply. This current right here has half a amp. Now using that current, we can find in here. So this current right here, we just found was half a amp. Now using that current, what we can do is find the total voltage. Remember, the voltage V1 was between these two nodes. As we went down, as we combined resistances, those nodes have stayed same. So V1 is actually across the 6 ohm resistor equivalent resistance is 6 ohms. That's why we get V1 is the current going through that 6 ohm resistance, which is I, 6 ohms resistance. So half amps times 6 ohm equals 3 volts. We figured out that V1 is equal to 3 volts. So that is 3 volts. Now we need to find V2. Now for V2, let's take a look at this. Now V2 is across this 5 ohm resistance. Now 3 volts is between this point and this point. So if we look at this, we have a voltage divider we have a voltage that's being divided between 25 ohm and the 5 ohm resistance, and between this point and this point is a total of 3 volts. So using the voltage divider equation, we get the voltage V2 across the 5 ohm resistor is equal to this resistance divided by the sum of the two resistances right here in series. So 25 plus 5, that's 30. So that's 5 ohms divided by 30 ohms and times the voltage between these two nodes, which is 3 volts. So we get 5 divided by 30 times 3, and that leads us to half a volt. Okay, so we figured out that V2 is in fact 1/2 volt.